Okay, I think I've learnt how to record using my visualizer, but I don't know how to pause it, so I'm just going to have to go for it, and if I make any mistakes we'll just have to fumble our way through. So we have got our first question, which is looking at chemical tests to identify different compounds. And the first thing it says is to look at the information in the table, identify solutions A, B and C. So solution A gives a yellow flame test, so yellow flame test immediately tells me it's sodium, and the gas produced is carbon dioxide when you add an acid, so it's carbonate. You are allowed to give symbols here. I will be posting the mark scheme up at the same time as posting up this video so that you can double check against that in case you've got anything different that you want to check it's on the mark scheme. B, brick red, so that instantly tells me it's calcium, and a white precipitate soluble in excess, so that could have been calcium or magnesium. It can't be aluminium, that dissolves in excess, but the brick red tells me it's definitely calcium, not magnesium. Then I get a white precipitate with silver nitrate, so silver nitrate is the test for the halides. A white precipitate tells me it's chloride. Metal ion in solution C, so I've got a dark green precipitate, so it's iron, or more specifically iron 2. You would get a mark for iron, you would not get a mark for iron 3 because that would not be green. Question 2, chromatography used to separate components of a mixture. I've got black food colouring and spots of known food colours to compare it with, and here is my diagram, and it's made 2 errors, so I'm looking for 2 errors in the setting up of this. So the first error I can see is the start line is drawn in ink, and therefore I would say start line in ink, and the reason that's a problem is because it would run or dissolve or split up or mix with the spots. So that's the first one. The second error that I noticed is that the solvent here is actually, the line of the solvent is above the line of the spots, so I've got the spots under or in the solvent, or the other way up, solvent above spots, so that therefore the spots will dissolve or mix with the solvent, or wash off the paper is accepted. So a different student has set up the apparatus without making errors, and here is what they managed. So what do the results tell me about the composition of the black food colouring? So the black food colouring is here and has gone up and separated into those 3 spots, and I've got substances A to E here, so I can instantly see that A and E are both in the black food colouring, so that's my first point. The second point is there's another colouring that I can't say what it is because it's not one of the ones that I tested again. So just saying there's another one is worth the second mark. I then have to get the RF value for colouring C. So to get the RF value, it's broken it down for me quite nicely there. I've got the distance from the start line to the solvent front. Now this is going to be really difficult for you because I'm guessing you've measured this on the screen, so we're all going to get very different values. Theoretically we should get the same ratio, but to be honest it stretches and squashes when you look at it on the screen, and even my printout is different to the mark scheme I've got, so my RF value is different to what they were hoping for. So we're just going to have to have a bit of common sense around whether you did this right. So I'm measuring that to be about 44 millimeters, and C I'm measuring to be around about 13 millimeters. Now when they give these spots like this, they're quite generous in the leeway as to what they allow. I always measure to the middle of the dot so that I'm well within the leeway that they're going to give me, but they do give a range on the mark scheme, as you'll see if you want to look at it, and the range is between 16 and 20, so it's a good 4mm of range they'll accept there. So the key thing then is that you're doing the distance moved by the colouring divided by the distance moved by the solvent, and that you're not getting your calculation the wrong way around. And the easiest way to find that out is if you have got a number less than 1. So the number I got was about 0.29, I think, from memory. So whereas the number that they got on the mark scheme was 0.40, is on the mark scheme, because obviously they printed it out to be a slightly different scale to the scale I ended up with. So whatever you ended up with, we're going to have to take that number forward with us now and use a bit of common sense, because we're all going to have slightly different numbers. So table 2 gives the results of an experiment on known food colouring in the same solvent. And you can see now that annoyingly it's split over 2 pages, but that final column basically here is the RF value, and that's what I need here. And it's asking me which could be C. Now according to my calculation, C would be erythrocene, but according to their calculation it should have been fast red. So again, you're going to have to use your common sense. Which one were you closest to, and did you actually understand the concept of this question, that you're matching the RF value? You could potentially have not got anywhere near any of these. You would get 2 marks for saying that it's none of them, because none of them are exactly the same RF value as the one you calculated. So that would equally be worth 2 marks. So there are 2 types of chromatography, gas chromatography and paper. Advantage of gas chromatography. It's easiest probably just to stick the mark scheme under the visualizer for this bit. So you can see here that the advantage of gas chromatography is that it's, well focused that, is it? Is that help at all? That's a bit better. So it's more accurate, more sensitive, only needs a small quantity of sample, it's quicker, faster, more rapid, and it can link to mass spec. So then you can find the masses of the different fractions that you separated your mixture into. Okay, and question 3. So, student investigated an eggshell and did some tests on the eggshell, and the table is split over the page again in my printout, which is annoying, but anyway, I've got a test and an observation. Ditch that. Okay, so I've got a test and an observation. They've added dilute hydrochloric acid, a gas was produced, the eggshell dissolved to a colourless solution. I've then taken that solution, which is now the eggshell with hydrochloric acid, tested it, flame test was red. I've then again taken that solution and added sodium hydroxide to it, white precipitate, not dissolving. I've taken that solution again, which is hydrochloric acid and eggshell, silver nitrate, and tested it, I get a white precipitate. And now I'm having to talk about those different tests and what they tell me. So they've said, how can I identify this gas in test 1? I've added acid to a substance, it's made a gas, so therefore according to my test that I've learned, that gas must be carbon dioxide gas, because it said that it contains carbonate ions. They've even given you a nice little clue there, haven't they? So therefore the test is lime water, bubbled through lime water. Sorry, I should have been a lot more specific there. So it's bubbled through lime water, and the lime water would turn cloudy or milky, or you'd get a precipitate. The student concluded the eggshell contains aluminium ions. Is that correct? So now I'm looking at this white precipitate that's not dissolving in excess. So therefore, oh sorry, and also aluminium ions, I've got a flame test here that's turned red. So I've got 2 bits of indication here that this is not going to be aluminium, because a red flame test is indicative of calcium or maybe lithium, and aluminium has no flame colour, and also a white precipitate, if it doesn't dissolve in excess. If it's aluminium, the precipitate would dissolve in excess, so therefore it can't be aluminium because the flame colour is wrong and the precipitate is dissolving in excess. That's my 2 marks for that. A student has said that it contains chloride ions. Is that correct? So you might think that sodium nitrate making a white precipitate would make me think it's got chloride ions, but back here I put hydrochloric acid in there, and that is the thing I'm testing, is silver nitrate hydrochloric acid. So of course it has chloride ions. It's got chloride ions from the hydrochloric acid, not necessarily from the compound that was in there. So no, this is not a correct conclusion because there is hydrochloric acid in there. Anyway, I'm now completely lost in my mark scheme. Okay, yeah, I found myself. So I said that with a bit of confidence. Okay, here we go. I think I know where I am. So some scientists want to investigate the amount of lead in eggshells. They use modern methods which were more sensitive than older methods. What modern methods could they have used? So there are a list of different ones you could say here. You could say mass spectrometry, you could say flame emission spectrometry, or you could say atomic, I need to slow down with my writing so you can actually read it, sorption spectrometry. And why would that be more sensitive? What do we mean by the word more sensitive? Well, it means you could actually test a smaller amount of a substance, or detect smaller changes, or use smaller sample sizes, something like that. This question then is quite a nice question for assessing that you know your iron test, because you're being given 4 colourless solutions, and we know they're one of these 4, but we don't know which is which. So what method could we use to find out which one is which? So initially I can see that one of them, the positive ion, isn't sodium. So the first thing I would say is to do a flame test, and sodium would be yellow and potassium is not yellow, would be fine. You wouldn't necessarily have to say what potassium does. So my first thing would be a flame test, and I would point out that sodium is yellow, and so therefore that would tell me that the one that, I mean, you could point out that potassium is lilac, but the point there being that it would then instantly tell me that the one that's not yellow is potassium carbonate. So I've found that one out. So now I've got 3 left, which are all sodium compounds, 2 of which are halides and one's a carbonate. So how would I test for a carbonate? So the second thing I would do, I would add an acid. I'm going to dilute nitric acid to all of them, and the one that the carbonate will fizz or bubble or effervesce or give off carbon dioxide. The sodium iodide and sodium chloride will not, so therefore I've worked out therefore now which is sodium carbonate. I've then got simply 2 which are halides, so the test for a halide, I've already added nitric acid, so I'm going to, if I'm worried about them not knowing that I've already added it, I will add nitric acid. This is why I chose nitric acid back here, because I knew the next test was going to be halide. So nitric acid, and this time I'm also adding silver nitrate, because if I'd had hydrochloric acid back here, they might have thought that I was testing with hydrochloric acid already in there. So nitric acid and silver nitrate, and then now if I have a chloride, I'll get a white precipitate, whereas if I have an iodide, I will have a yellow precipitate. So that has enabled me to work out which of those is which. Again, I'm going to post this mark scheme up at the same time as the video so you can double check that. I think what I might do now is just stop this video and start again on the next page, just to gather my thoughts.